turn is right. Anybody new today? One. Just one. Okay. Okay, so I think that today I'm going to start with the new material, integration by substitution. I emailed the material to you this morning, and I also emailed you the answers in green this time, not yellow. So do something about it. Come on, be better. So everybody take one and send the rest back for the others. Take one and send the rest along, and so on and so on and so on. Hopefully everybody's here now. So last time, 2 days ago, we were solving integrals using the invariance of form of the differential. In other words, if we could notice something in this form might look like f of u derivative dx, or if we could build the derivative of some function, if we had enough material to see that we can see a function inside the function u, inside the function x, the internal function u, and then we see a factor which is actually the derivative of that internal function, then we can change it into a simpler function and apply the basic principle of invariance of form, meaning all we need to do is integrate the function f. Basically what we did was we more or less dragged this function into the differential if we move this way. So again, the old reminder for you, the differential of a function u is the derivative of that function times the differential of x. Again, I would like to remind you, do not lose dx or du or dt anywhere at all. If you have the integral sign, it must contain dx, the differential of the independent variable, or well, whatever serves as the independent variable in the integral. So if you want to get the function out of the differential, if you want to find the differential of the function, then you derive. If you want to get a factor into the differential, then you integrate. I've been sketching this for a while now, I think. Every time, every single lecture, this happens. Sometimes, though, we don't see the derivative of an internal function anywhere. Sometimes the situation looks more complicated. It's not so obvious. So if this is obvious, or almost obvious, all we need is some number to multiply by. So if this is obvious to the accuracy of a constant factor, then it's simple to do like this. If it's not obvious, if you can't actually see explicitly the derivative of something that's in there already, then we have to do a little artificial trick, which is called the method of substitution. Although these two methods flow one into the other, they are very, very close, and sometimes it's difficult to say which of the two methods is applied because they're practically the same in that function, for instance. So what we do sometimes when we see a function f of x dx, and it's complicated enough so that we don't really understand how to integrate it. In that case, sometimes, again, not always, sometimes we can use a substitution. The general idea of a substitution is we denote by a new variable, t, or you may call it u if you like, some expression in terms of x, then we express x as some function from this. We express x as a function of t. So we are introducing some new variable. Usually it is some part of that expression. From that expression now we express x in terms of t. So now I have x equals phi of t, some kind of function, some kind of expression. So I choose t to be a part of that integrand, the function inside the integral, and then I express x from there. Of course I have dx, so I can write dx is d of phi of t, which means it's phi derivative dt. It's phi derivative. So now I can replace the original function. Now I can replace this by f of x is expressed in terms of t, f of phi of t times dx can be written like this, phi derivative of t dt, and now we basically have again the same old form, the same thing. We have f of u prime dt. Well, the basic variable, the name of the basic variable has changed, but at least we have something like f of u times u derivative times the differential of the independent variable, which has changed for now. Normally, in most cases, or in most complicated cases, I will give you a hint, I will tell you what kind of substitution we might use. In some situations, as you get used to this idea, you will be able to guess. And the thing is, if you guess at, well, which part of this function will we denote by t? If you make a wrong guess, if nothing good happens, then you can always change your mind. Okay, that didn't work, let's choose something else. No problem. Of course it takes time. Of course sometimes you get a waste of time. But this is how these things work. This is how these things work, and it's basically, we can't do anything else. So I will begin with the second example for a very simple situation. For example, if we have x times 3x minus 5 to the 7th power dx, something like this. One way of doing this would be, of course, find the power, expand this. Those of you familiar with Pascal's triangle would probably know how to expand this. 8 terms, a long expression, multiply everything by x and integrate term by term. That's always possible if you have patience for that. If you don't have patience for that, I'd say it would be nice if we had a single variable to the power 7. Makes things much easier. So, alright, let's use a substitution. 3x minus 5 substituted by t. T is 3x minus 5. So, of course, to put it there, we will need to express x as well. X as a function of t. Now we are doing this phi of t thing. X would be t plus 5 divided by 3. So this is what corresponds to this part. We express x from that substitution. The next part that we have to do, we have to find out how to replace dx, derive the phi function. So dx will obviously be, as we can see, it's t over 3. The factor at t is 1/3, so the derivative, not the integral this time, we are deriving. The derivative of t over 3 is 1/3 dt, of course. And now I can simply substitute things in here. So instead of x, I have t plus 5 over 3 times, this is t to the 7th, this is 1/3 dt. Slowly, step by step, we substitute the expressions x by what we had in terms of t, 3x minus 5 by t, now we have t to the 7th power, dx now is 1/3 dt. Actually, it's also possible to differentiate both sides of this, then from this, for instance, that's another possibility. How can we get this? If this seems too difficult, we could write dt must be, differentiate this 3 dx, and from there, obviously, dx is 1/3 of dt. You can do it this way. It doesn't matter in which form you differentiate both sides, whichever seems more convenient to you, and then express dx in terms of dt. So now we could simplify this. Obviously, I could take 1/9 outside the integral. Then I have t to the 7th times t plus 5. That would make t to the 8th plus t, 5t to the 7th dt. And now, yes, we can integrate this. This is not painful anymore. So now we have 1/9 times t to the 9th over 9 plus 5t to the 8th over 8 plus c. Now we can simplify a little bit. We can even try to get everything on the same line. We can try to get everything on the same line. So it would be 1/9 times, okay, 72, 8, 9. So it would be t to the 8th outside. So now we have 8t plus 4 by 9, 45, something like this. It's not strictly necessary. We can plug back this expression into t in this form. It's not strictly necessary to put everything on the same line. But you can do this. You can factorize it. This is factorizing actually means writing the final answer in the simplest form possible. But as it is, I will already be happy if you can substitute t equals 3x minus 5 back here, and that's it. As it is, of course, I have to write 6, 3, 6, 4, 8, t to the 8th, so 3x minus 5 to the 8th power times 8t is 24x minus 40 plus 45, so it's 24x plus 5 plus c. So it's possible to simplify it to this form, but as I said, I will accept this 3x minus 5 to the 9th, 3x minus 5 to the 8th instead of this. So it doesn't really matter. I'm simply showing you how it's possible to simplify the expression, and I would advise you to do it in the t form before you plug the x expression back into this, because that makes things easier in this form than write 3x minus 5, 3x minus 5, and then try to simplify. That will be more difficult. So basically, at this point, we have finished integration. At this point, we have the integral. Of course, we have to put x expression instead of t, so the final answer is still one step away. Or you may choose to do this if you prefer things neat and nice. So why did we do the substitution? It's obviously because it's much easier to multiply a single power by a sum. It's easier to multiply a single power by a sum than a single variable by an unpleasant power of a sum or a difference. Obviously, it's much nicer if we have a single variable here and a simple-ish, well, it is simple, a simple expression instead of x. So the form changes, but, well, it's not it's not different in principle. It's still the 8th power, expression of the 8th power, so it's in principle it's not much different. But the form it's written now is much easier, much more easier to integrate. And that's our purpose, to make things easier to integrate. Okay, any questions about this? Before I move on to the next example. No questions? Okay. Next example, all right. X squared dx over square root of x plus 4. Again, something that looks bad. We can't really integrate it in the way that we used last time on Tuesday, because I don't really see the derivative of this anywhere. I really do not see the derivative of x squared anywhere. It's under the, okay, it's x under the square root, under the radical, but it doesn't make things easier. So obviously I would like to make some kind of substitution here. What is the obvious substitution? You can't take an expression that's too complicated, but you can't afford to take something that's too simple. For instance, we might choose to take x plus 4 for t, or we might choose to take square root of x plus 4. Whichever. So here I did square root. Okay, let's do square root. At least we get rid of the square root for a while, for a short while. So we will do t is the square root of x plus 4. Again, it corresponds to choosing a substitution. Some part of the original function is chosen to be replaced by t. Now the next part, we express x from there, so x becomes a function of t. In this case, x will become t squared minus 4. Square both sides, subtract 4. Now we can express dx. So now we see dx will become 2t dt. When you differentiate both sides, you find the differential of both sides. And now, obviously, we can start changing the integral. So we have performed these three important things. Now we put everything back and see what happens. So x squared would be t squared minus 4 squared. This is x squared. dx is 2t dt. And the square root below the line is replaced by t. Now, aren't we lucky? We are. So in this case, fortunately, t gets cancelled out, and basically we get a square of a binomial. So if we expand it, if we open the brackets, we can integrate again. It doesn't always cancel out everything, but in most cases, it becomes easier to integrate anyway. So in this case, I take 2 out of the integral, and now I have t to the 4th minus 8t squared plus 16 dt. Simple to integrate. 2 times t to the 5th over 5 minus 8t cubed over 3 plus 16t. And now all that's left is put this back instead of t. And that's all. And that's all. So I can write, okay, 2/5 square root of x plus 4 to the 5th power minus 8/3 square root of x plus 4 to the 3rd, and plus finally 16 square roots of x plus 4 plus c. So the last step is just substituting back. So the thing is that it's not always very obvious, but in most cases it's fairly obvious what we should choose for t. Obviously this the less pleasant part of the function inside the integral. Otherwise, there is no sense. Otherwise, it doesn't make any sense. No, there's no need to do that. All right. So now, I think in exercises, in number one is something that we do just like we did. My first example, which is example 2 on your paper. Exercise 2 can be done in a similar way, although, well, it won't be bad. 3, I have given you a hint. 4, hint again. You are allowed not to take my hint and do it in your own way if you don't like that. If you don't like to use that particular substitution. There are other substitutions possible. In the answers I sent you, I think there are three of these integrals are ones that you don't know how to finish off. Well, I'm perfectly willing to show you, but we will deal with those methods in the coming 2 weeks.
Sorry,
Yes.
to multiply 2 only by 1/5.
To multiply for 2.
Oh, 32 there, and 16 there.
Yes.
Yes, thank you. I will do so now. So it's 16 and it's 32. All right. Okay, try it, and then if you need me to show you any specific integral out of these 14, that's fine. Just let me know, I'll do it. I suspect that for many people there are still quite a few integrals left over from last time. Well, not for you, okay, but for other people probably. I don't have the illusion of believing that everybody has finished all the integrals from Tuesday. So if you need me to show anything specific, just let me know and I will do it. So
Number 10.
those who were absent on Tuesday, I have here the paper, the integration using the invariance of form of the differential. I did email it to, well, there are a couple of people whose email is bouncing back. So if you need, this is for Tuesday, if you need